Live. Guy. One person I join. Guide me. Oh yeah, join guys, join guys. I'm waiting for you to join before we begin. All right, okay. You're joining. Hi, I'm seeing you. 1, 2, 3, 4, 5. Okay, all right. Oh, how far, Jay? After see, I don't start the life. Guy, I've been lost. But they guide me. No go. I follow John a bit because, like, I don't even know other people here what they talk. I beg John, I beg. All right. Okay, guys, join up. We are starting in the next 2-3 minutes. We are starting very soon. We're starting very soon. Very soon. Very, very soon. Okay. Okay, column 9. All right. Somebody left. Okay, J. All right, so we are starting right away. Please, there's something I want us to do regarding this experiment number 7. I want to believe you all have your graph sheets. But before we look at the graph sheets, I want to be sure you're following what I'm doing. I want to be very sure. So I want to be sure you're following what I'm doing. I want to be very sure you're following me. Don't forget, this is experiment number 7. And the theory behind experiment 7 is the visible atomic spectrum of hydrogen. Now, there is a lot of theory here, but we are not going to go over the theory. We are going straight to the calculations here. We are going straight to the calculations, and this is what I want you to do. First things first, these are the equations we are going to be using. We're going to be using these equations here. I'm going to start with the very first equation. Now, if you go through the manual, now turn to page number 65. Turn to page 65. Turn to page, are you all hearing me? All right. So turn to page 65. You can see equation number 7.1. So this is the very first equation we are going to be using, equation number 7.1. So let me write out equation 7.1 for you. So look at equation 7.1 here. So you have this equation here. You have 1 over lambda. You have 1 over lambda. 1 over lambda is equal to 1.097 times 10 raised to power minus 2 nanometer minus 1 into, please check this out, into 1 over n1 squared minus 1 over n2 squared. Close this bracket. So this is the very first equation we are going to be using. We are going to be using this equation first. So you can call this equation equation 1. Now the second equation we are going to be using here is this equation. Look at it. You can call this equation 2. We're going to be using the equation that says that delta E is equal to HC over lambda. So this H is a small h, HC over lambda. So these are the two equations we are going to be using for this entire experiment. Now, I want you to turn to your data sheet first. Turn to your data sheet. Your data sheet is found on page. Your data sheet is found on page. Check this out. Turn to page, page number 73. This is your data sheet on page 73. Now, let me show you what you're going to do here. Let's just get straight to the point. Now, if you look at this data sheet, we have helium here. We have hydrogen. So we are only going to be very interested. Okay, I'm coming. Okay, I'm with you. All right, so let's continue. So now if you're on the data sheet, we have two columns here. We have the helium column and we have the hydrogen column. So you're going to be plotting a graph, but let me show you how you're going to do it. First things first, if you look at the wavelength found on the helium column, if you count them, they're going to give you about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. There are 13 wavelengths here on the helium column. Then if you go to the scale reading, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 values each on the wavelength column and on the scale reading column. Now, what are we going to do with these values? These values here, we're going to use these values to plot a graph. Now, let's check out the values first. From the helium column here, or let me say from the wavelength column, we have the highest value to be 706.5. And if you go to the lowest value, you have 396.4. So we're going to take this into consideration when choosing the best scale for our graph. So that is how to do it. Then for the scale reading, you have the highest value to be 11.1 and you have the lowest value to be 2.1. So this is going to help you to select the best possible scale for your graph. So the first thing we are going to do here, we are going to answer question number 1 under the calculations. So I want to be sure you are seeing the calculation aspect. It says that we should prepare a calibration curve. Prepare a calibration curve for your spectroscope by plotting your scale readings against the known wavelength of the helium lines presented on the data sheet. So these are our helium lines. Or let me say, these are our helium line here. This and this. These are helium line. So you're going to plot a graph of wavelength against scale reading. You can still plot a graph of scale reading against wavelength. You are still going to get the same answer. So let me show you how to do it now. Let's get right into it. Let's get right into it. So this is what I'm going to do. In my Fusca paper, I can just write out the values for the wavelength for helium. So I can just do this. Check out what I'm going to do. All right, I'm with you. So check this out. Let's say we have, now look at the values we have here. We have 396.4. We have 402.66. We have 412.0. We have 414.4. 414.4. Hello? All right. So I have 414.4. I have 438.8. Just take your time. 438.8. Then I have 447.1. 447.1. Then I have 471.3. 471.3. Then what again do I have here? I have 492.2. 492.2. Then I also have 501.6. 501.6. Then I have 504.8. 504.8. Then I have 587.5. 587.5. Then what do I have next? I have 667.8. 667.8. Then I have 706.5. 06.5. All right. Now look at these values I have. These are the values for my wavelength. So I can call it lambda, or let me just write wavelength. So those are my wavelength values. Now let us now look at the values for the scale readings. Now I'm going to merge the wavelength values with the scale reading values because they are both 13, and we're going to use it to plot our graph. So for our scale reading, we have 11.1. So 11.1 corresponds with 396.4. So let me call this scale reading. So that's my scale reading. So I have 11.1 for that. Then for the 402.66, it corresponds with 10.1. So you have 10.1. Then the next one here, we have 9.5. 9.5. The next, we have 9.3. 9.3. After 9.3, we have 7.9. 7.9. After 7.9, we have 7.5. We have 7.5. After 7.5, we have 6.5. 6.5. After 6.5, we have 5.8. After 5.8, what do we have next? We have 5.6. 5.6. So after 5.6, what do we have after 5.6? We have 5.5. All right, so after 5.5, we have 3.7. We have 3.7. So So after 3.7, we have 2.5. We have 2.5. And after 2.5, the last value we have here is 2.1. So that's the last value, 2.1. All right, so now we are going to plot a graph. Check this out, please. Check this out. We're going to plot a graph of wavelength against scale reading. If you look at the instruction we have here, look at the instruction we have. It says, prepare a calibration curve for your spectroscope by plotting your scale readings against your known wavelengths. So by right, scale readings is supposed to be on the y-axis and the wavelength will be on the x-axis. But don't forget what I told you earlier. You can do vice versa and you still get the same answer. Now let us now plot this graph. Let me show you how to plot the graph. So I'm going to do a very rough work first before I get right into it. So my graph is going to look like this. Check this out. I have this. Okay, sorry. Okay, I have this. This is a sketch. I have this. So this is my scale reading. And this is my wavelength. Before inserting the values, let me tell you what this experiment is all about. So we want you to plot a calibration curve of scale readings against wavelength for the helium lines presented here. So after plotting this graph, this is what you're going to obtain. Now don't forget scale readings here, wavelength here. Now your graph is going to look like this. Look at what I just did here now. Now, your graph is going to look just like a curve. This is a curve here. This is a curve. You're going to have a curve. Now, don't forget, I told you earlier that you can use a flexible broomstick to obtain this curve. So you can use a flexible broomstick to obtain this curve. And once you're done obtaining the curve, it's going to look just like this. And that is the end of your graph plotting. Now, you might be asking, why are we giving these other values here? I want to just summarize the graph before I start plotting it. So after plotting the graph of this against this, or this against this, it's going to look just like this. So once you're done, these other values you have here, look at, these are the scale readings for the hydrogen spectrum. The curve we are preparing is for the helium spectrum. Look at the curve here. The curve is for the helium spectrum. So after plotting the curve for the helium spectrum, we are now going to use the scale readings from the hydrogen spectrum to do our analysis. Now, what kind of analysis are we going to do here? Now, check this out. We are done with our curve now. Now, if you look at the scale reading values presented on the hydrogen spectrum, we have 4 scale reading values. And what are they? We have 9.7, we have 8.3, we have 6.0, and we have 2.6. Now, these are our scale reading values for the hydrogen spectrum. So what are we going to use these values for? Now, we are going to do this. We are going to go straight to our curve. Now, our curve is ready. This is our curve here. It's ready. Now, we'll now go to the scale reading axis of our curve. We'll go to the scale reading axis. We are going to locate 9.7 on the curve. Once you locate 9.7 on the curve, for example, it's going to look like this. Let's say these are 9.7 here. Let's say I got 9.7 here. I will trace a dotted line to meet the curve. Then I'm going to trace it down to locate the exact wavelength value on the x-axis. So once I've located that, I am going to record that value here. Look at it here. It's written wavelength from calibration curve. So you're going to record that first wavelength value here on this dash. Once you're done with that, you now go straight to the next scale reading value, which is 8.3. Now for the 8.3 value you are seeing here, you go back to the curve. Now this is our curve here. Now this is our curve. Now for our curve, I'm going to locate 8.3. Now let's say my 8.3 gave me something like this. Let's say this is my 8.3. I'll trace it down here. Once I get to this point with a straight line, I'm going to use a ruler for that. Once I get to this point, I'll trace that value down with a ruler to locate the exact wavelength value on that particular axis. Once I've located that value, I'm going to put that value as the next value here. That's the second value now. That's my wavelength value. So after putting that, I want to be sure you all are following. All right, so now after putting that on the second dash here, now you're going to do the same thing for the third dash and for the fourth dash using wavelength values of 6.0 and what? And what? 2.6. I don't know if I'm communicating. So that is exactly what you're going to do. So now, meaning that you're going to have 4 of these lines here. Check this out. You're going to have 4 of these lines. So I trace this to this. I take it down. I have a value here. And that's the third value here. That's the third value here. Then I'll now do the last one, which is 2.6. So I'm going to locate 2.6 on the scale reading axis. Do the same thing there. Trace it down. Now, once I'm done with this now, I'm going to conclude my graph. And that is all I'm supposed to do for my graph. I want to be very sure everyone on this live is following what I'm doing. If you are following what I'm doing, please reply by sending me, yes, I'm following. I want to see. All right. All right. All right. Yes, I'm following. Yes, I'm following. Yes, I'm following. Okay, I'm seeing that. That's really great. I'm happy you guys are following this. I'm happy you guys are following this. Then next, let's get straight to plotting the graph. Let's get straight with the plotting of the graph. All right, let's get straight to plotting the graph now. Okay, yeah, let's get to plotting the graph. So I couldn't buy the green graph I talked about, so I'm going to be using a red graph sheet for this for this live. So I'm going to be using this red graph sheet. I want to believe you all have your graph sheets. I've not really gotten any information from them, but you can use the graph sheet here. You can use this one here. That is, if you can use this one here. Use this one here. But if you want your work to be a bit neat, say a little neater than usual, you can use this type. But I prefer green graph, but you can still use red. If red is available, use red, no problem. That's fine. Okay. All right. So now let's get right into it. So I want to plot my graph. I want to plot my graph now so that you guys will see how my graph will look like. I'm very sure that Bros J has already taught you guys how to plot graph. So I don't know. Am I supposed to teach you how to plot graph again? Okay. I guess we are okay with that particular aspect. So let's get right into plotting the graph. Let me get my pencil and pen. Get my pencil. All right. All right. Okay, I'm right back. So let's plot the graph. Now, before plotting this graph, I am going to mark my axis. Now, this is how I want my graph to look like. Before I even start plotting the graph, I will have to first of all check out my values. There's something I'm going to do now. Regarding the wavelength axis. Now, please, I want everyone to observe this. I'm going to do something very different regarding the wavelength axis. Now, this is what I'm going to do. If you notice, the values of the wavelength did not start from 0. I don't know if you notice something like that. They did not start from 0. So let me show you how your graph will look like if you don't follow what I'm going to show you. Now, check this out. Let me use a blank sheet for it. Now, let's say this is your graph sheet. This is your graph sheet now. Your graph sheet is like this. And these are your axes. You have, this is your, let me show you. Check this out. Let's say this is your graph sheet. All right, now check this out. Now, if this were to be your graph sheet, and let's say you put your wavelength here, this wavelength, and this is a scale reading here. This scale reading. Now, you want to plot the graph. Now, remember that the values of the wavelength did not start from 0. Now, the smallest value on the wavelength axis is what? 396.4. 396.4 is not 0. So if you want to plot this graph, what are you going to do? Now, somebody that wants to start from 0 will say this is 0. Whatever here, whatever here, whatever here. Let's say this is 50. Now, check this out. 0, let's say this is 50, 50. This is 100, 150, 200, 250, 300, 350. Then you have what here? 400. Now check this out. Now it is very obvious that the very first point of this graph is going to be somewhere here. Check this out. So your very first point is going to be somewhere around here. So meaning that your curve is going to be running away from your graph. Check this out. Your curve is going to be looking like this. And this is your graph sheet. So you wasted this entire area doing nothing with it. And you are plotting your curve on this side. So your graph will look so horrible. So I want everyone here to avoid making this mistake. That is why I want to give you this humble suggestion. And what is that? Now, since your values here does not start from 0, you can ignore 0. What did I say? You can ignore what? Ignore 0. So how are you going to ignore 0? Let me show you something. This is how you're going to ignore 0. Please, I want you to pick this. It's very important to pick this. Pick this. Pick this. So you are going to ignore 0 by doing this. Once I'm done with this now, I'm going to be talking about how to select the best scale for this graph, because you need to use the best scale so that your curve will make sense. Okay, now let's say I'm going to do it. Okay, let me just do it. Don't worry. Let me use this side. It's still the same thing. All right, now let's say this is my x-axis. This is my x-axis. Now, since my values are not starting from 0, I can do this. Check this out. I can do this. Now, these are my regular lines. So check out my regular lines. These are the lines on my graph sheet. Lines on my graph sheet. Lines on my graph sheet. Whatever. Lines on my graph sheet. So what will I do from here? Now, I will just do this. Check this. I'll just do this. Check. I'll do this. Now, what am I trying to do here? I'm trying to show that I don't want to start from 0 because my values don't start from 0. Are you with me? So I cannot come down here now and start from where? I cannot just start from what? 350. After 350, I have what here? 400. 400 are 450, 500, 550. Then I'll have what here? 600, 650, 700. Whatever, 750, and I'm done. And that makes a lot of sense because this side is showing that your graph does not start from 0. So in order for your graph not to look like this, you have to do this. So just do this and let your value start from 350. You can even start from 300. It's still fine. It's not bad, but it depends on the scale you are using. All right. So let's get right into it. Then another set of assumptions I would like you to also make. Please look at these assumptions here. Look at these assumptions. Please follow me. Look at these assumptions here. For this 396.4, I can never find this value on my graph. Let me tell you, no matter how big your graph wants to be, even if your graph wants to be as big as a whiteboard, you will not find 396.4 on your graph. So we are going to do something that is called approximation. We are going to approximate because there are some values you will never find on this graph. And what are those values? Now, look at what I'm going to do. So this is my table. So I have wavelength. I have, after wavelength, what do I have? I have scale reading. Wavelength, scale reading. All right, so let's do this together. Now, the first wavelength value I have is 396.4. Now, you are going to round this up to the nearest value you can find on your graph. So since I have plotted this graph a million times, I know that the nearest value you can find on this graph from 396.4 is 400. So I am going to call 396.4 400 as I'm plotting my graph. So I'm going to record 400. Oh, sorry, I'm going to write 396.4. Now, in bracket, I'm writing 400. Do you know why I'm writing 400 in bracket? Because I know that I will not plot 396.4. What I'm going to plot on the graph is 400. Sure, you get right? I'm going to plot 400. Now, the next value I have here is 402.66. Now, you cannot find 402.66 on that graph. You can't even find 403. 403, you can't find 403 on the graph. You can't even find 404. But you can find 405. So I am going to approximate this to the nearest whole number on my graph sheet, which is 405. But if you don't want to approximate to 405, you can just probably plot 402.5. It's still fine. So in place of 402.66, I'm going to be plotting 402.5, or I can even plot 405. It's still the same thing. Now let's go to the next value, 412. You can't find 412 on the graph. What I'm going to find on the graph is 410. So in place of 412.00, I'm going to plot 410. Now, the next value I have is 414. There is no 414.4 on the graph. Instead, you have 415. So I can just round this up and plot 415. So 414.4. What I'm going to plot is it 44? Yeah, 0.4. I'm going to plot 415. Or I can still limit my value to 410. I'm still going to get the same answers. Now, what about the next value here? Now, the next value I have here is 438.8. 438.8 is not on my graph. It's not there. Okay, sorry, it's not in my graph. So what I do, I'm going to plot 440. So in place of 438.8, I'll plot 440 because I can find 440 on my graph. Then check this out again. Check this out. Now, what about 447.1? I can't even find 447 on my graph. Instead, I can find 450. That's the nearest whole number there. So in place of 447.1, I'm plotting 450. Plotting 450. Now let's go to the next value. You have 471. 471. Look at 471 here. 471.3. 471.3. Now in place of 471.3, I'm going to plot 470 because that's the nearest whole number I can find on the graph there. Now followed by 492.2. Now 492.2 is not on the graph. It's not on the graph at all. But I can find 490 on the graph. Let's move on to the next. So after 492.2, I have 501.6. 501.6. Now in place of 501.6, I'm plotting 500 because that's the nearest whole number to 501.6. Then after that, look at 504.8. 504.8, the nearest whole number here is 505, which I can find on my graph. So 504.8, I'm plotting 505. Your graph will be so beautiful, I bet you. Now, let's check the other one. That should be the last. No, that's not the last. I have 587.5. Guess what? This value is on the graph. I'll show you. It's on the graph. But in case you don't like it, you can plot 490. Sorry, 590, still the same thing. So 587.5 is still on the graph. I'll plot 587.5 because I can find it on the graph. And moving on. Then the next value is 667.8. Now for the 667.8 here, let me see. Yes, I can plot 670. 670. So 67.8. I can plot 670. That's the nearest whole number there. Then the next thing we are going to, that's the last one, 706.5. 706.5. So for 706.5, I'm going to be plotting 710. That's the nearest whole number. And these are all the values you're going to be using for the wavelength axis. What about the scale reading axis? Now, guess what? The scale reading axis does not have any problem because you're going to find all the decimal values in that graph. Check this out. The first value there is 11.1. The second value there is 10.1. The next value is 9.5. Is 9.3. Next one is 7.9. The next one is 7.5. The next one I have here is 6.5, 5.8. 5.8. Let's be a little fast. 5.6, 5.5. 5.5. 3.7, 2.5. 3.7, 2.5. Then the last value I have here is 2.1. Now let's plot the graph. I'm ready to plot. Are you ready to plot? If you are ready to plot the graph, stay with me. Let's plot the graph. All right. So I'm going to be using my scale reading. Now, check this out. I think I'll prefer putting my, let me check. I prefer putting my scale reading on this side. Let our scale reading be on this side. Let me put it here. It's still the same thing. Or let's just put our scale reading here. Here is still fine. Let's put our scale reading here. So draw your lines. Draw your lines. So let me start from this down. Let me start from here. Let me check whether I'm on track. I want to be sure I'm on track. So if I start from 0, because my scale reading is going to start from 0, it will start from 0. So if this is to be my 0, 0, then I'm going to have 0. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't start from there. Let me start from here. Let me start from here. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I think this place is okay. Or you can still start from here. Here is still okay. In fact, let me start from here. The 11.1 will not be an issue. Let me start from here now. So I'm going to thicken my line. But guess what? Based on what I told you something earlier, that for the x-axis, that is the wavelength axis, I'm not going to start from 0. So let me just draw my line now and keep. Look at it. My zigzag line. I'll stop here. It's okay. I'm okay. So let me now thicken my lines. Let me thicken my lines. See what I'm going to do here. Let me thicken my lines. All right. My lines are thick. So you use a very dark pencil for this. Make your lines thick. Then let me draw the lines for the y-axis. For the y-axis, I'm drawing my line now. Let me draw my line now. All right, okay. All right, my lines are ready. Now let's choose our scale. So what is the best scale for this graph? Now look at the scale here. Scale. Look at the scale. Now for the, we are not going to be calling this X and Y axis, but for the sake of this class, let me call it X and Y axis is fine. Let me call it X and Y axis. So don't forget that for this graph, our Y axis is scale reading. So I'll say scale reading axis. I'm using 1 cm is to what? 1 unit. So I'm using 1 cm is to 1 unit. Now for the other axis, that is this one here. Let me not select something yet. Let me check my values out. My highest value is 710 and my lowest value is 400. So I can start from 350. So if I start from 350 here, 350, 400, 450, 500, 550, 600, 650, 700. That's a perfect scale. So I'm going to record here as 350. 350, 400. Check this out. 350, 400. I want to be sure you are seeing this. Are you seeing this? Okay, you are seeing it. You are seeing it. You are seeing it. So 350, 400. So the next one is what? 450, 500, 550, 600, 550, 600, 550, 600, 650, 700. I'll stop at 700. Guys, I just discovered something now. I just noticed something on this graph. This graph I'm using, I think this graph is 22 cm. It's not just 1 cm, it's 22 cm I'm seeing here. So the graph is 22 cm. Check it out. You can see that the distances are so large. So this is 22 cm each. So each of these blocks is made up of 2 cm, not just 1 cm. So I can just adjust my scale a little. I can adjust my scale a little. I can't find that paper again. Let me check. Okay. So I will adjust my scale a little. So I will adjust my scale a little since I've just discovered that stuff now. So look at my scale here. Scale. I'm using 2 cm is to what? Is to 1 unit. On where? On scale reading. Yes, on scale reading. So 2 cm is to 1 unit on scale reading. That is, my graph is very large. You know what I mean here. Then on the other axis, which is here, I'll be using 2 cm is to 50 units. Or you can just say 2 cm. 2 cm is to 50, not units this time, 50 nanometers, because your wavelength is in nanometers. So 2 cm is to 50 nanometers. So this is my scale. Now let's plot the graph. Please take note of this scale. Take note of the scale. 2 cm is to 1 unit on the scale reading axis. And this is on the wavelength. On the wavelength axis. So I'm done. Let's plot the graph. Or should I give you 15 minutes to plot this graph? Or do we plot it together? If you want us to plot it together, please respond. Let's plot it together. Let me know what you're doing. Then if you want me to give you 15 minutes, then tell me, give us time to plot the graph. I don't die. I don't die. Oh boy. Okay. Oh yeah, let's do it together. Let's do it together. Uh, you guys have it. You have it. Let's do it together. All right. So now for my scale reading axis, let me put in the values there. So I'm starting from 0. Don't forget this 0. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, I'm on track. So let's start from 0. So this 0 here, right? Yes, that's 0. Okay. Let me check something. I can still decide not to even start from 0. Are you aware? I can still say I will not start from 0, but it's fine. Let's just start from 0. No wahala. So this 0, this is 1, 1.0. This is what? 2.0, 3.0, 4.0, 5.0, 6.0, 7.0, 8.0, 9.0, 10.0, 11.0. No wahala. This graph, there's no problem with the graph. The graph is okay. No problem with it. I think we are good to go. Now, let's now plot this graph properly. Let's go back to the table of values, the one I gave you. Let's go back to the table of values. Who is stealing all my papers? Okay. What's going on, man? Okay, I'm coming. All right, so let's plot the graph together now. Let's plot it together. So now, see, please, I want to appeal. If you are reporting this on your data sheet, please, use these values here. As in, that is, I'm saying, if you want to present a table in your foolscap before plotting the graph, these are the values you're going to write. But while plotting the graph, you are plotting these values in brackets. So you can just pen this down in your book, in your rough book, plot the graph. But after plotting the graph, if you want to report your answers, please, this is what you report. You plotted this against this. Now let's plot the graph. So I have 400 against 11.1. So I'm plotting. So this is 400 here. Remember, look at this. This is 350. This is 400, right? Good. Now, I am going to trace this 400 up. There's even only tracing 400 up. Look at it. See 400. Look at the line. The line goes of 400, 400, 400. And I'm plotting at where? 11. That's 11.1, right? So, 11.1 is not here. So I can just plot, just drop it here. It's still the same thing. This is the beginning of my curve. My curve is going to start from here. And it's going to look so good. All right, so I've plotted my first value. I'm going to plot the next value now. Now, the next value I'm going to plot is 402.5 and 10.1. Now, let's check this out. So now, check this out. This is 350. Now, let me show you something. Are you aware that each of the lines in between, check this out. Each of the lines in between, this is 350, right? Let me show you something. This is 350. Now the lines in between, after 350, what the next line here is what? 355, 360, 365, 370, 375, 380, 385, 390, 395, 400. So each of the lines there represent 5. Take note. So each of the lines in between here all represent what? 5. Don't forget that. Now we are going to plot 402.5. 402.5 is found here. Now check this out. Check this out. This is 400. This is 400. Now the next line is 405. In between 405 and 400, that space there is 402.5. You can still plot 405, no problem. It's an approximate value. So I'm plotting that line, and I'm plotting that line against 10.1. 10.1. Let's plot that together. So I have this. Okay, I'm plotting that line against 10.1. This is 10 here. Don't forget that because of the scale we are using for the scale reading axis, each line represents 1. Check this out. This is 1, right? This is 1. Okay. Now the next line after 1.0 is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2.0. So each of these lines represents a 0.1 or 0.1 on this axis. So I now know where my 10.1 can be found. Where is my 10.1? Now I'm plotting 405. If you want to, you can still plot 402.5. It's still fine. So trace the line up here. This is the line. Look at the line here. This is the line here. Yes. So I'm plotting 10.1. 10.1 is the next line here. Look at it on top here. All right. My graph is already making sense. Check it. I already have 2 points. Look at 2 points. They're almost close to each other. Now let's continue the plotting. Now the next plot you're going to have is 412, which is you're going to plot 410. 410 against 9.5. So where is 410? Check 410 out. After 400, the next line is 405. The next line is 410. So the next line is 410. So I'm plotting 410. I'm plotting 410 against 9.5. Now I'm sure we all know where 9.5 is, right? So trace this up. Locate 9.5. This is 9.0. This is 9.0 here. Now 9.5. This is 9.1, 9.2, 0.3, 0.4, 0.5. Look at 9.5 here. Check it out. This is 9.5. So I'm plotting 410. Look at 410 line here. Yeah. All right. So I've seen my point. All right. So I have 3 points now. I've marked 3 points already. Look at 3 points. I marked 3 points. Please, I want to be sure everyone is following. If you are following, please just respond, I am following. I want to be sure you are following. Okay, I've seen a question. Someone is asking, sir, what if you write the plotted values beside the given values? No, don't write it. Don't write the plotted values beside the given values. So simply write only the given values, but you are going to plot your own values because that is what your graph is going to give to you. All right, so if you are following to this point, let me know. Just respond by saying, I am following. I want to be sure everyone is following. All right, all right, all right. I'm seeing that. I'm seeing that. Okay, okay. All right, you're following. Let's move on now. So I've plotted 3 points together. Now let's plot the 4th point. I want us to plot the 4th point all together. Let's plot it. 4th point. The 4th point is 438. I want to be sure. 1, 2, 3, 4. No. The 4th point is 414.4. 414.4. Now I'm going to be plotting 415 against 9.3. Let's check it out. So where is my 415? Let's check. 415 is the 3rd line after 400. The 3rd line after 400. 1, 2, 3. I've located my 3rd line. Then we are plotting it against 9.5. Is it 9.5? No, sorry. 9.3. 9.3. So let's do that together. So I can see my 3rd line. This is 9.0, 9.1, 9.2, 9.3. It's too close to this. This is not bad. Let's plot it. It's fine. Look at my point here. It's too close to the other value. If your points are looking just like this, you are on the right track. Let's continue. Let's go to the 4th point. So for the 4th point, the 5th point now. 1, 2, 3, 4, 5. So look at the 5th point. You are plotting 438.8. You are plotting 440. 440 against 7.9. Now, check it out. Where is 440? 440 is 2 lines before 450. 2 lines before 450 is 440. Let's do that together. Or you can just count it manually till you get to 440. So I'm plotting 440 against 7.9. Let's do that together. This is my 7. 7.9 is the last line before 8. So you can trace it to this side and look for your 440. 440 is 2 lines before 450. That is it here. I have it. All right. I've plotted it. Guys, you can see that, right? I've plotted it. I've plotted it. I've plotted it. So I've plotted 5 points out of... So once we are done plotting this graph, I will show you the shortest method of plotting the graph. But for now, let's plot the graph. Let's do it together. Let's do it together. So where are we? Where are we? We are about to plot the 5th point, or sorry, the 6th point, which is 447. We are plotting 450 against 7.5. Check it out. 450. Where is 450? Look at my 450 line here. Look at 450. So I'm plotting 450 against 7.5. So you take it up to 7. 7.5, okay? Look at 7.5 here. So I'm plotting right here. If you can see this, that's 7.5. So I'm plotting there. All right, I've plotted. You can see that, right? Aha. So we have how many points? 1, 2, 3, 4, 5, 6. Let's continue. Let's go to the 7 points now. The 7th point. 1, 2, 3, 4, 5, 6, 7. 470. We are plotting 470 against 6.5. Let's do that together. 470 against 6.5. Where is 470 here? After 450, let's count. 450. You have 455, 460, 465, 470. Okay. Okay. I've seen 470. So use your ruler. Follow this line. So 470 is the 1, 2, 3, 4. The 4th line after 450. So follow that line up. Take it up and plot it against 6.5. So I'm following the line up. I want to plot it against 6.5. Look at 6. Okay. Look at 6. I've seen 6.5. Okay. 1, 2, 3, 4. I've seen it. I've plotted. Check this out. All right. I just plotted that. I just plotted that now. All right. I want to believe you're all following. So let's continue the plotting. So we have just a few more points to finish. So we just plotted 470. Let's now plot 490 and 5.8. I'm going to be very fast now. 490 and 5.8. Where is my 490? Where is my 490? So after 450, you have 500. So where is 490? 470, 475, 480, 485, 490. 490 is 2 lines before 500. 2 lines before 500. Let's do that together. So 2 lines before 500 is 490. And I'm plotting that against 5.8. Okay. 5.8. I've seen 5.8. Okay. I've seen it. All right. Hoping that you've plotted that. Now we are heading straight to 500 and 5.6. 500 and 5.6. This is my 500 line. Locate 5.6. This is 5. 5.1, 2, 3, 4, 5, 6. All right. I have another 2 set of points that are close together. So the next point you're going to plot is next set of points. I'm plotting 587.5 and 3.7. 587.5 and 3.7. Where is 587.5? Where is it? 587.5. Okay, after 550, you have 555, 560, 565, 570, 575, 580. All right. 580 is 4 lines. 4 lines before 600. 4 lines before 600 is 600. 1, 2, 3, 4. Yeah, so all right, so that's it here. Oh yeah, trace it till the top and mark. Sorry, it seems I missed that. Let me check. 587.5. Sorry. So this is 580. I've not even gotten to 510.5. So I have 550, 555. 560, 565, 570, 575, 580, 585. After 585, the space in between 585 is 587.5. Either you pick that space or you simply plot 590, no problem. So either you pick that space or you plot 590. Okay, let's plot 590 to avoid errors. 590. So I'm plotting 590 against what? Against 3.7. Against 3.7. It seems like I have skipped a point. I have skipped 1 point. I just skipped a point now. We skipped 504.8. Nobody reminded me of that. Okay, thank you. I've seen it on the comments. Okay, I've seen it. Yeah, thank you. 505. Thank you very much. So we skipped 505. So I'm going to plot 505 against 5.5. So where is 5 there? The next line is 505. So I'm plotting 505 against 5.5. All right. So let's check it out. This is 5.0 and this is 5.5 here. All right. The 2 points are very close. They are very, very close. Let's carry on. So the next point I'm going to plot now is the one I just talked about last, which is 590. Let's plot 590 against 3.7. Let's plot 590 against 3.7. Look at my 590 here. Let's take it up to 3.7. This 3.0 here. I've seen 3.0. Let's locate 3.7, 3.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. All right, look at it here. Please, this stuff is taking quite some time because my light in here is really disturbing my eyes. But I think let's just manage. All right, so let's now go to the next, which is 670 and 2.5. 670, 2.5. 670 and 2.5. So I've seen 650 on my graph. 650. So 655, 660, 665, 670. I have my 670. So 670, I'm plotting against 2.5. In case I'm finding it difficult to locate what do you call it? To locate 670. 670 is the fourth line. 1, 2, 3, 4. Yeah. The fourth line after 650, that's 670. So locate that line, you trace it up and locate 2.5. So let me find 2.5. This is 2.0 here, and this is 2.5. All right. Let me see. 1, 2, 3, 4. All right, I have it. All right, so I'm almost done. Then let's get to the last plot for today. 7.1. So look at 700. Look at 700 here. 2 lines after 700 is 710. 705, 710. 705, 710. And plot 2.1. So take it up. Locate 2.0 here. The next line is 2.1. All right. I'm done with my graph. Now the next thing is for us to join the points together. Now look at this. From what we've plotted, it is very obvious that we are going to obtain a very smooth curve. Check it out. We are going to obtain a very smooth curve. Now, this smooth curve we are going to obtain, like I said, you can use a broomstick or you can use a French curve. French curve might not really give you all what you want, but me now, I can use a short trick. Look at what I'm going to do. Let me show you something. Check this out. Or let me turn this like this. I want to be sure you're seeing what I'm doing. So look at what I'm going to do. Look at what I'm going to do. I'm going to use something like a free hand, but you can use your flexible broomstick. But someone will need to hold it for you before you can do that. Or you can just use a French curve at once. You get. Check this out. So I'm going to do this. I'm going to do this. I'll just use a dotted line. I'll try using a dotted line to connect the ones that I want to connect, though, because it's not all that will connect. See what I'm doing? See what I'm doing? Somebody can draw a small curve that will just come out like this. And it's very fine. It's okay. It's very, very okay. Now, for the sake of our class here, I am going to join this curve together. But I am not saying that all the points are going to enter. All the points will never enter. Some stubborn points will shoot out. I think about 3 or 4 points are going to shoot out. So in the end, you are going to, you are going to have something that looks like this. Let me just join this. This is just for teaching purpose. I'm saying for illustration purposes. If I'm to plot the real graph with my French curve or a flexible broomstick, you see it coming out very well. Look at a very nice curve. Check it out. My curve is very nice. Check it out. Okay. Now, the hard part of the whole assignment, we've just done it now. Now, I'm not going to go through the rigorous process of teaching you how to label your graph. I'm sure you can do it. But in case you cannot, I think I will do mine and I will send it to you guys on a platform. So this is all about the graph. Let's now answer question number 2 from the... Please, if you have questions to ask from the graph, please let me know. Let me know. If you have questions to ask, just indicate. I'm waiting for questions here. Okay, no questions. Okay, no questions. So yeah, let's move on to question number 2. Now, question number 2 here says, okay, don't worry. We are done with question number 1. Now we are done. You have plotted the graph. Number 2 says, if you have your manual, please refer to page 72. That's where we are now, page 72. It says, using your calibration curve, determine the wavelength of each of the 4 hydrogen lines. Record these wavelengths on your data sheet. Let me take it again. Using your calibration curve, determine the wavelength of each of the 4 hydrogen lines. Record these wavelengths on your data sheet. Let's do this now. I think I've already explained this earlier, but let me just do it. Now, what are the 4 hydrogen lines given to us? Look at the 4 hydrogen lines. We have 9.7, 8.3, 6.0, and what? 2.6. Now, we're going to use these values now. The first value is 9.7. Now, go straight to your curve. Now, this is my scale reading axis. Look at my scale reading axis here. Look at the scale reading. Now, let us locate 9.7 on this curve. Where is 9.7? This is 9.0. Look at 9.0 here. Take it up. 9.5. After 9.5, 2 lines after 9.5 is 9.7. So I have this 9.5, 9.6, 9.7. Look at 9.7 here. I just marked it. Now I'm going to draw a straight line from 9.7 down here to meet the curve. Check this out. So this is going to meet my curve. Dotted lines will meet my curve. Now, once dotted lines meet my curve, I'll locate that point and I'll draw it down to meet my x-axis, that is the wavelength axis. I'm going to see the corresponding wavelength there. Okay, I think I've seen it. Mine is at 405. Mine is at 405. So from that point, draw a straight line down. All right, so I'm having 405. Now, the 405 is just obtained from here now. Remember, the lines I drew now, these lines must be visible on your graph. Look at it. Mine is very visible. Look at it. Mine is visible, starting from the point of 9. Look at it. It's visible. Are you seeing it? All right. So, and I'm having 405 because I'm having the line after 400. All right. So you go down here. Check this out. You go down here. You write 405. That's what you're going to write here. 405. Now, check this out. If you get 410, you are 100% correct. Now, your value should range between 405 and 410. Please take note of that. Your values must range between 405 and 410. Have you taken note of that? If you've taken note of that, please say I. Okay, sorry, just drop a hi on the group. Or just drop done. Let me repeat myself. I said your values must revolve around 405 and 410. Done. Okay. Done. Okay. Done. Okay. One more done. Then we'll move. One more done. I want to be sure you're done. Your values must revolve around 405 and 410. All right. Let's move on to the next slide. Now, you're going to repeat this same method. You're going to repeat this same thing. Now, I'm going to engage everybody. Let me engage you now. I want you to, use what you plotted to get me the corresponding values for 8.3, 6.0, and 2.6. 8.3, 6.0, and 2.6. Let's start with 8.3. For 8.3, what are you going to have? Check 8.3. Check 8.3. Drop your answers. For 8.3, drop your answers. Let me see. For 8.3, if you're done, drop your answers. I'm waiting. While I do mine, let me do mine. 8.3. This is 8.0, 8.1, 8.2, 8.3. So this is my 8.3. Okay, look at mine here. You can take it down and check what you're going to have. Any answer? 430. 430 is good. 430 is good. 425 is good too. 430 is good. 425 is good. No. 425 is good. 430, 425. Let me check mine. I'm coming. Let me check mine. Let me see. 405, 410, 415, 420. Mine is 425. Mine is 425. That's where my line is going to be at. Mine is 425. So mine is 425. If yours is who is giving me 428? How did you get 428 on this graph, please? I don't think you can get 428 from this graph. I don't know the graph you're using. You can't get 428. I'm seeing 428 on the comments. That's not possible. So you can get 425 or 430. 430 is fine. No, 428 is not okay. You can't get 428. But 428 is still not bad because it still revolves around 420 to 430. So it's still fine. But I'm surprised how you got 428 from that graph. I don't know how, but it's fine. It's okay. Let's continue. So the next value we are going to do for now is 6.0. It seems I saw someone that dropped 6.0, 480. Let's check. 6.0. So look at my 6.0 here. Look at my 6.0 here. All right, look at my 6.0. Okay. Okay, now I'm taking it down. Okay, I'm having this 500, 95, 90, 85. I'm having 485. I'm having 485. I hope you're recording these values down, right? I'm having 485. I'm having 485. So look at okay, 485. So I had 405, 425, 485, and I'm having what again? Check. So the last value for this, I have 2.6. Let's check for 2.6. That's the last. Then we'll start solving mathematics now. 2.6. This 2.0. Let's go to 2.5. Okay, I've seen 2.6. For 2.6, let me see. 2.6, sorry. Okay, for 2.6, I have this. See. So for 2.6, let me check. Okay, that's the point here. Okay, I'm done. I have 650, 655, 660, 665. I have 665. I have 665. I have 665. Let me check. Okay, somebody has 675. 675 is fine. 660 is still fine. Okay. Okay. I don't want abrupt values. You guys are doing very well. I'm happy. You are doing very, very well. I so much like your values. Now, since we are done with this graph now, let me now show you how to arrange your answers. We are done. We are done. So this is how to present your answers. Now, this is how to present your answers. So for question number 1, done and dusted. Done and dusted. Question number 1, done and dusted. So we don't have any business with question number 1 again. We are now going to question number 2. For question number 2, it says, using your calibration curve, determine the wavelength of each of the 4 hydrogen lines. Record these wavelengths on your data sheet. Now, first things first, go to your data sheet, record those values here, record them here. 1, 2, 3, and 4. Record all of them here. Once you're done recording the 4 of them here, come back to your full scarp. Now, let's assume that these are our full scarp. These are our full scarp sheets. So I am now starting from question number 2. After you've written your name, whatever your name, department, manual number, etc., etc., this is your full scarp sheet. I will now say question 2. Question 2. Now for question number 2, what am I going to do here? I'll start by saying scale reading. Look at it. Scale reading. Then I have wavelength. wavelength from calibration. Calibration what? Calibration curve. Wavelength from calibration curve. All right. Draw your line. Do this. So what was the first scale reading value you had there? 9.7, 8.3, 9.7, 8.3, 8.3, 6.0, 2.6. All right, so these are all what you have. And for 9.7, I got 405. If you got 410, write it there. 8.3, I got what? I got 425. 6.0, let me check. What did I get for 6.0 again? 6.0, what did I get? Can't find my paper. Okay, for 6.0, I got 485. 485. And for the last one here, I got 665. I'm done with question number 2. I'm now going to question number 3. Question 3. So how will you answer question number 3? Let's go to the manual. Question number 3 says, using equation 7.3, determine the amount of energy, delta E, associated with each of the 4 wavelengths in the hydrogen spectrum. Record these energies on your data sheet. Now, there is no column here for energy. So the data sheet they are talking about here now is your foolscap sheet. Now, how are you going to get these energy changes? Now, these energy changes are called delta E. Now, delta E is reference to equation 7.3. So if you go to equation 7.3 in your manual, look at equation 7.3 here. Look at equation 7.3. Look at it. Delta E is equal to HC over lambda. This was the second equation I wrote down for you in our class today. So we are going to use that equation to find the energy change associated. Look at it here. I think I wrote it down today. All right, so we are going to use this equation now to find, pay attention, we're going to find the corresponding energy associated with the 4 wavelengths we calculated. Now let's do that together. So I'll start by saying from equation 7.3, delta E is equal to HC over lambda. Are you there? Where our H is equal to Planck's constant is a constant, 6.63 times 10 raised to the power minus 34 joules second. Then your C here is the speed of light, which is equal to 3.0 times 10 raised to the power 8 meter per second. So these are constants. So after stating all this, you now go straight to the point. You now say delta E1. That's the first energy you're considering. Now this energy is associated with delta E1 where lambda 1 is equal to, what's lambda 1? That's the first value of your lambda. That's the first wavelength you obtained, which is 405. All right, so delta E1 where lambda is equal, okay, is equal to that. So delta E1 now is going to be equal to, let's substitute, HC over lambda, 6.63 times 10 power minus 34 joules second times, what is C? 3.0 times 10 power 8 meter per second. I'm dividing by what now? By lambda. Now, what is the value of my lambda? 405. Don't forget that these values are in nanometers. Nanometers, nanometers, nanometers. So you have to convert nanometers to meters before you can use it to solve here. So how do you convert from nanometers to meters? Now, if you want to convert 405 nanometers to meters, you are going to, multiply by 10 raised to the power minus 9 meters. All right. You multiply this by, okay, just like saying I don't want to waste time. Just simply say 405 multiplied by 10 raised to the power what? Minus 9 what? Meters. I'm sure you know what will happen based on dimensional analysis. The meter will cancel the meter. Now the per second cancels the what? Per second, meaning that your final answer here is going to be in joules. So someone should punch it and give me the answer. What will you get from here? Someone should do this. Drop the answer in the comments. I want to check. Someone should do it. Drop the answer in the comments. Someone should do it. Someone should do it, please. Someone should do it. Someone should do it. No answers. Okay. No answers yet. Okay, I think let me use my calculator for this. It seems we don't have our calculators handy. Seems we don't have our calculators handy. Let me try it out. So 6.63 multiplied by 3, okay, divided by 405, okay. Okay, my answer is 4.91, okay. So you're going to have 4.91 multiplied by 10 raised to the power 18 joules. Check it out. That's the answer in joules. Now let's do that for the second one. So you are going to repeat the same calculation for the 4 wavelengths. That is all what question number 3 is asking for. So you can just say delta E2 will be equal to HC over lambda. This is even a waste of time. So just substitute 6.63, 10 raised to power. Exactly. I think I have that. 6.63 times 10 raised to power minus 34 times 3 times 10 power 8 divided by, what's the value of our second wavelength? Our second wavelength is what? Is 425. So I'm going to say 425 times 10 raised to power minus 9. All right. All right. So what will you get from here? Let's check this one out. Let's do it together. So I'm going to be doing 6.63 multiplied by 3 divided by 425. So I'll have 4.68. So 4.68 multiplied by 10 raised to the power minus 19 joules. So this is my delta E2. Now, if you notice, I'm not really going through the rigorous process of trying to, convert this thing back to standard form, because we all understand how to change this to standard form. So it's not necessary. So I'm just going straight to the final answer, and that's all what we need. So delta E3 is equal to 6.63 times 10 power minus 34 multiplied by 3 times 10 raised to the power 8 divided by, what is the value of my lambda 3? 485 nanometers. So I have 485 times 10 raised to the power minus 9 meters. I'm converting to meters. All right, so what do we do here? Oh yeah, fast. So the same calculation, I'm doing 19. Sorry, that's a mistake. 6.63 multiplied by 3 divided by 485. So I'm going to have 4.10. So I'm having 4.10 times 10 raised to the power minus 19 joules. So there's no time. That's my delta E3. Let's go to delta E4. Now for delta E4 is equal to what? Still the same calculation again. 6.63 times 10 raised to the minus 34 times 3 times 10 power 8. I'm dividing by the last wavelength, which is 665. All right, 665 times 10 raised to power what now? That's minus 19. So what will be the final answer here? In the same fashion, so I have 6.63 multiplied by 3 divided by 665. So I have 2.99. 2.99 times 2.99, yeah, times 10 raised to power minus 19 joules. So we are done with question number 3. Let's go straight to question number 4. Exactly. You are doing very... No. I'm seeing 10 raised to power minus 20. That's wrong. No, that's not correct. Now, all your powers are going to be 10 raised to power minus 19, not minus 28. Now, in case you don't find this calculation straightforward, you can go check out your law of indices. It will really help. All right, let's continue with question number 4. I think we are almost finishing this. Now, question number 4 is very technical. Very, very, very technical. Very technical. So I'm going to show you a shorter approach to doing question number 4. A very short approach. Someone is asking whether we can watch the video after now. Let me check whether I'm even recording this. I'm coming. Let me check. Okay, so let's continue with the calculation now. Now, let me show you how to do question number 4. I'm done with question number 1 to 3. Let's do question number 4 now. I think we are almost finishing. I think what I'm going to do is that for the experiment number, for experiment number, what do you call it again? Number 9, we might not be able to do it this night because of time. So I think I will just do it tomorrow, and I will tell you when I will do it after this live. This live will be finishing in the next 20 minutes. Let me round off. I'm almost done. All right, so let's go to question number 4. Question number 4 says that, let me check question number 4. Question number 4 says, use equation 7.1 to determine the level from which the electron fell to N1 equal to 2 to produce the emission. Record this level on your data sheet. Now, we are going to do a very serious mathematics because I don't want this number 4 to take us a long time. I want to do something very quickly now. Something very, very quickly. Something very, very quickly. Now, please, everyone should look at this. Look at what I'm going to do now. Look at what I'm going to do. Look at what I'm going to do. Now, we have that 1 over lambda. We have that 1 over lambda is equal to 1.097. Okay, let me not use 1 point. Okay, let me not use this. Let me not use this. Let me just use R. So we have 1 over lambda is equal to what? It's equal to R into 1 over N1 squared minus 1 over N2 squared. Now, for this question now, we are actually looking for N2 because the question has provided us that N1 is equal to 2. We know the value of R, to be 1.097 times 10 raised to the power minus 2 per nanometer minus 1. So R is a constant. It's called Rydberg's constant. I will explain all this when we start treating this topic, quantum theory of the atom. But for now, let's just solve the problem. So N1 is equal to 2, R is equal to that, and lambda, this lambda you're seeing here, is equal to the lambda you've been provided with, or let me say, the lambda you obtained from the graph which you plotted. All those 4 wavelength values, they are the values you're going to be using here. So since the objective of this equation is for us to find the value of N2, I wouldn't want us to be beating about the bush. So let's simply make N2 the subject of the formula so that we can use it straight in all our calculations. So how do we make N2 the subject? I will just open this bracket. I will open this bracket, or simply I'll divide both sides by R. So I have that. I'll divide both sides by R. Okay, or let me just cross multiply. So I have that 1. I'm cross multiplying, I'm doing this. So 1 is equal to lambda R into 1 over N1 squared minus 1 over N2 squared. I'm just solving math. I'm sure all of you knows what I'm doing. All right, I'm just solving mathematics. So I'm going to divide both sides by this. So that will be 1 over lambda R is equal to what? Is equal to 1 over N1 squared minus 1 over N2 squared. Okay, now if you notice, since I've already divided both sides by lambda R, so it has made this bracket to open. So the bracket is already open. So I can just leave it open. It's already open. So I'm going to like make this one the subject of the formula by taking this one over to this other side, and that will be 1 over lambda R minus 1 over N1 squared is equal to minus 1 over N2 squared. All right, I don't know if you're following this. Okay, so what are we going to do next now? So the next thing we are going to do is that we are going to, let me see. I think we are going to take the LCM. We are going to take the LCM of this. Okay, no, we are not going to take the LCM. We are just going to make this one a subject of the formula. So therefore, we have that N2 squared is going to be equal to 1 over lambda R minus, sorry, this stuff has a minus sign, minus what? 1 over N1 squared. All right, I think we are making headway now. So from here, don't forget, you are not writing this in your book. I'm just trying to derive this so I can use it for this class. So let me see. Okay, so making sense. This is N2 squared. So for me to remove this minus is going to enter here and turn this to the other side. So what I'm going to have now is I'm going to be having that N2 squared is equal to square root of 1 over N1 squared minus 1 over lambda R. Please write down this equation. We're going to be using this equation for all our calculations today. Now write down this equation. So the squared is already gone because you have taken the square root of both sides. So let's use this equation for let me write out the equation. Let me write it out. Okay, now look at the equation again. So N2 is equal to square root. N2 is equal to square root of 1 over, this is the simplest equation we can use instead of beating about the bush, 1 over 1 over n1 squared minus 1 over lambda r. All right, let's solve together. So question number 4. Question 4. So what do we do in question 4? For question 4, you say lambda equal to, what's the first value of lambda we got? What was the first value of lambda? It was 405 nanometer. So if you got your lambda to be about 410, still use that 410 here. I'm going to show you something. Still use 410. I have a reason for telling you that the lambda values must range between a certain limit. So for lambda 1 must range between 405 to 410. I don't think it should be 415. 45, 410 is fine. Let's try it out. So from what we have here, let's put it back into this place. So you're going to have that when lambda is equal to 405, n2 is going to be equal to square root of 1 over, don't forget that n2 is equal to, is given as 2. N2 is given as 2. So 1 over 2 squared, which is equal to 4, minus 1 over lambda r. What's our lambda? Our lambda is 405. Don't forget, our lambda is 405 times, what is my r? Now my r is equal to, check this out, is equal to what? 1.097 times 10 raised to the power minus 2 nanometer minus 1. So you can just change this to an ordinary decimal to make sense. Ordinary decimal will be something like 0.0, let me see, 0.1097. But let's check, does it work? Is it the same thing? 1, 2. No, that's a lie. It's not the same thing. It should be 0, just 0. It's going to be 0.01097. 1, 2. All right. It makes a lot of sense. So let's use that instead. 0.01097. Now let's solve this together. Now I'm going to solve it step by step. I'm going to solve it step by step to avoid making mistakes. I'll solve it step by step. Now look at the very first thing I'm going to do here. I'll start by saying 1 over 4 is 0.25. So I'll go to this side and work this side out. And this side is going to be 40, let me check it out. 405 times 0.01097. 0.01097. Okay, 405 times that will give me 4.44. 4.44285. All right, that's my answer. So I'll say 1 divided by 4.44285. So I'm having 0.225. So I have 0.225 there. Now this 0.225 I'm having here, I'm going to be doing 0.25 minus 0.225. And what would that be? Okay, 0.25 minus 0.225. That gives me 0.025. All right. So 1 divided by 0.025 will give me 40. That's giving me 40. So I'm not going to find square root of answer. What is the square root of 40? Check. What is the square root of 40? If you're active, check the square root of 40. Drop it in the comments. I want to see. What is the square root of 40? Drop it. Let's see. What is the square root of 40? 6.33. Beautiful. So N2 is equal to 6. Final answer. N2 is equal to 6. So we are selecting the nearest whole number. We are rounding it up. So 6.33 is equivalent to what? 6. All right. 6.3. All right, so now you're going to do the same thing for lambda when lambda is equal to 425 nanometer. Your N2 still remains 2. All things being equal, you are going to solve this same problem again. And how are you going to do it? Repeat the same thing. In that case, N2 is going to be equal to, repeat what I just did, 1 divided by 1 over 4 minus 1 over, my lambda is now 425 times 0.01097. Someone should do this and give me the answer. Someone should give me the answer for this one now. Someone should give me the answer for this one. Yes, I like that. You guys are on track. Someone should give me the answer for the second one. Now, this is how you're going to be doing it. And you'll be getting your answer straightforward. There is no time for wasting time. So, what will be the answer to this one? Or do we do it together again? Okay, let's try. So, I'm using my phone. So, I'm starting from, 425. So, you're going to do the calculation step by step, or else you won't get the answer. So, I'll start by saying 425 multiplied by 0.01097. I have an answer. 4.66225. 4.66225. Okay. So I'm going to find the inverse of that. 1 over 4.66225. So 1 divided by 4.66225. So I'm having 0.214. Check this out. 0.214. Beautiful. I love that. Somebody just solved it. It's 5.13, which is approximately what? 5. I love that. So the answer here is going to be that N2 is equal to what? 5. Guess what? Now, when you now go to the next one where lambda is equal to 4, what's the third value of lambda again? Can't remember. What's the third value of lambda? Someone should drop it on the comment. Let me see. What's the third value of lambda? What's the third value of lambda? Someone should drop it on the comments. I want to see. I want to be sure you're following this calculation. What's the third value for lambda? No comments. I'm waiting. 485. Beautiful. We are going to use 485. So lambda 485. We are going to do the same thing here. Don't forget that our N2 is still equal to 2 and every other thing remains the same. So in that case now, my N2 will be equal to square root of 1 over 4 minus what? Minus 1 over, lambda is 485 multiplied by what? I'm multiplying this lambda by what now? By 0.01097. And that's all. So if I do this, I'm going to have that my N2 is going to be equal to 4. Then after someone should do it. I want us to verify whether the answer is 4. Do it, fast, do it. Do it and give us the answer to be 4. Let's verify something. The answer is going to be 4. Do it, check. 4.01. That's beautiful. The answer is 4. N2 is equal to 4. So we've done for how many? 3. It's remaining one more. So when lambda is equal to, what's the last value for lambda? Someone should drop it for us. Someone should drop the fourth value of lambda for us. Let's verify something. What's the last value for lambda? The fourth one? No. It's not 485. Check. I want to be sure you're following this calculation. What is the last value for lambda? 665. That's beautiful. So lambda 665. That's it. So 665, and we are having that the value for N2 still remains what? 2. All right. So let's solve. So what is the value of sorry, that's N1. Sorry. So the value for N1 remains 2. So what's the value of N2? It's going to be equal to square root of 1 over 4 minus what? Minus 0. Oh my God. minus minus 1 over 665 multiplied by 0.01097. Let's do it together. So what is the value for N2 here? What's the value for N2? N2. What's the value for N2? N2 is 3. That's beautiful. N2 is 3. Have you noticed a pattern here? Have you noticed that the corresponding values of N2 are, you have 6, 5, 4, and what? 3. Now, let me tell you a secret. Now, this is the secret behind this graph you are plotting. I want to show you something. This is the secret behind the graph you're plotting. If you have data on your phone, I would like you to go on Google, search for something. I want you to search for the 4 visible lines of hydrogen. I want to show you something. What are the 4 visible lines of hydrogen? Or, you know what? Let's use our chemistry textbook to check. What are the 4 visible lines of hydrogen? Because hydrogen has 4 visible lines. And these 4 visible lines occur at 4 corresponding wavelengths. What are these wavelength values? Let me take you to Ebin and Gammon. Let's verify the answer from there. Let's verify the answer from Ebin and Gammon. And I'll be getting my answers from chapter 6 or so. Chapter 6. Under quantum theory of the atom. I want to show you this. You would definitely like it. Because this graph you're plotting must correspond to what I'm going to show you now. Okay. I think I'm there now. I'll show you something. I'm there. Let me look at the chart. Yes, look at the chapter here. Look at the chapter Quantum Theory of the Atom. Now I'm going to show you something. I'm going to show you the 4 visible lines of hydrogen, where they occur at. You see it. Let me locate it. Okay, the textbook does not present it that well. It doesn't present it well. I don't know why it's not here. So let's just get our answers from Google. Let's get our answers from Google. There's something I need to show you. What are the 4 visible? You can go to Google, type, what are the 4 visible lines of hydrogen? Let's check it out. Then you will see that the graph you plotted was not a waste of time. Check it out. What are the 4 visible lines of hydrogen? Who has seen the answers? Drop it on the comments. Let's see. What are the 4 visible lines? If you've seen the answers, drop it. Let's see. What are the 4 visible lines of hydrogen? Okay. No answers from you. You've dropped it. How come I can't see it? Who said I've dropped it? But I can't see anything. I can't see it though. Okay, you can do that later. You discover that the four visible lines of hydrogen occur at 410, 410, 430, within that range, 485, and 665. If you check the corresponding wavelengths for the visible lines of hydrogen, you will get that particular value. You get that particular value there. So look at this answer here. Check out this answer. Okay. These are approximate values though. Look at this is 656, 656 nanometers red, 486 nanometers blue, 434 nanometers blue. Okay, this 410. You can see 410 here, right? So the graph we plotted was a waste of time. 410, 434, 486, and what? 656. But from our graph, from the nature of our graph, our values are 100% correct. Now, what will make you to understand that the values are correct is the fact that you got these answers 6, 5, 4, and 3. So we are almost concluding these experiments now. So this is the end of question number 4. Let's now answer question number 5. So for question number 5, it says, in fact, for question number 5, we are now summarizing all the answers we've got for today. It says, as a means of correlating these data, indicate the electron transition and associated energy for each of the 4 wavelengths on the diagram on your data sheet. Use the diagram at the end of the background information as a model. Now, what diagram are we talking about? Now, look at this diagram here. Let me show you the diagram. Okay, it's not here. Look at the diagram we're talking about. So we are using this diagram. Check out this diagram. Check it out. See what you're going to do. Now you're going to correlate all your data, everything you've done for today. Look at it. So you're going to be doing this. So everything you calculated for today, you just drop it here. Let me show you how to do it. Now check this out. Let me show you how to do it. So question number 5. Question number 5. That's the last for today. So regarding experiment number 9, that will not take us time. I'm going to do that tomorrow in details. That should be around 1 hour. So I'll do that around 1 hour. It won't take us too much time. So for question number 5, question 5. Question number 5. Now do this for me. Get your ruler, draw 6 lines with your ruler. You're going to draw 6 lines in total with your ruler. So I'm drawing 6 lines with my ruler. Check this out. I'm drawing. Okay, you can just draw 5 lines. 5 lines is fine. But I'm going to draw 6 lines. Check this out. I'm drawing 1. That's line 1. Then I'll give a space. I'm drawing 6 lines in total. Line 2. Draw line 3. Line 3. So I'm drawing line 4 now. I'm drawing line 5. Okay. I'm drawing line 6. Most of these lines, you might not use them, but I'll show you what to do with it. I think I've made a mistake there. Damn. It's fine, it's fine. All right, so I'm sure you're following what I'm doing, right? So I'll call this n is equal to 6. N is equal to 5. N is equal to 4. N is equal to 3. N is equal to 2. And n is equal to what? 1. So what are we trying to do here? We are trying to show the transitions, because if you notice, the electrons here, we are undergoing transitions from higher energy states to lower energy states. If you go back to that question number 4, those calculations you did, you are practically assuming that the electrons fell from somewhere to a lower state, which is n equal to 2. So they fell from somewhere to a lower state, which is n equal to 2. So the question is, where did they fall from? And that is the values we calculated in question number 4. We got 6, 5, 4, and 3. So you are trying to say, in essence, that the electrons fell from 6 to 2. The other one fell from where? From 5 to 2. The other one fell from 4 to 2. The other one fell from 3 to 2. That is basically what you're saying. Now, I'm going to illustrate all this information using this diagram. How? Now, I'm trying to say that the first electron fell from 3. Check this out. It fell from 6 rather. So this is 6. It fell from 6. Where is my 2? Look at my 2 here. So it fell from 6 down to 2. And I'm going to use an arrow to represent this. It fell from 3 to 2. Now, while it was falling, pay attention. While it was falling from 3 to 2, what was the associated amount of energy here? You just simply use the illustration given in the manual. E is equal to this, right? Good. Simply say, when it fell from this to this, it gave out this amount of energy. E, you can say E is equal to, what was the value of E for the first transition? Check out your calculations. Drop the answer in the comments. What's the value of E for the first transition? That is the first value of E we calculated for. Check. What was the first value of E we calculated for? Drop in the comments. Let me see. Okay. Now let me check. Let me check something here. Let me check something. Okay, I think I've seen it. All right, check. So look at my delta E1 here. Look at my delta E1. The first value of energy I calculated for was what? 4.91 times 10 to the power minus 19 joules. Exactly. So that's 4.91 times 10 to the power minus 19 joules. Now go to the next one. So now the next electron or the next electron transition was from 5. From 5, it fell to 2. From 5, it fell to 2. Now, when it fell to 2, what amount of energy was emitted? That is delta E2. Delta E2 is given as 4.68 times 10 to the power minus 19. 4.68 E is equal to 4.68 times 10 power minus 19 joules. All right, now let's go to the next transition. The next transition was from 4. From 4, it fell to 2. Now, during this transition, what was the corresponding amount of energy? That is delta E3. Now, delta E3, we calculate it to be what? The delta E3 here. Delta E3 is 4.10 times 10 power minus 19. So you have 4.10 times 10 power minus 19 joules. Now, the last transition is from 3 to 2. That's the last transition there. From 3, it fell to 2. So from 3 to 2, we have, that is the last delta E value we did, which is 2.99. 2.E is equal to 2.99 times 10 to the power minus 19 joules. Now, this is all about this experiment. Now, once you've drawn this diagram like this, this is all they want you to do. So this diagram is reflecting on the point, on the fact that the first electron moved from 6, which is the higher energy state, and it fell to 2. And when it fell to 2, it gave out this amount of energy. Now the next transition was from 5 to 2, and this is the corresponding amount of energy. The next transition is from 4 to 2, this is the corresponding amount of energy, and the last transition from 3 to 2, and this is the corresponding amount of energy. So this is all about experiment number 7. So arrange the answers in a foolscap. Make sure that your graph is very neat. Endeavor to title your graph, and that is all you are going to be doing for this experiment. So we won't be doing the next one, which is experiment 9. We'll be doing that tomorrow. So I will arrange a time, and the time should be this same time, 6:45. So by 6:45 p.m., we are going to start experiment number 9, and I'm going to do it in detail so that you'll be able to submit it on Wednesday. If you have questions, drop it in the comments. If you have the questions, please drop it in the comments. I am here to answer. If you have questions, drop in the comments. I'm going to be answering you now. Okay, sir, please, how did we have minus 19? All right, let's do the indices now. Let's do the indices. I'll be responding to all your questions now. Let's do the indices. Okay, what was the first? Don't forget, delta E is equal to what? Delta E is equal to HC over lambda. Remember, right? And H is equal to 6.63 times 10 power minus 34 joules second. Okay? And C is equal to 3.0 times 10 raised to the power 8 meter per second. And our lambda, we had 4 values for lambda. Let's use lambda 1, for example. Lambda 1 is equal to 405 nanometer. Convert this 405 nanometer to meter, because your calculation has to be dimensionally correct. If it's dimensionally incorrect, you will not be getting the correct answer in this case. So I'm going to convert this to meters. And converting from nanometers to meters is by multiplying the value in nanometers by 10 raised to the power minus 9. Why? Because 1 nanometer is equal to 10 raised to power minus 9 meters. So I just didn't want to go through all these conversions to avoid wasting people's time. So I'm doing it now because I'm done with the entire work. So I don't waste anybody's time. So 1 nanometer is equal to 10 raised to power minus 9 meters. Are you there? So if you want to convert from nanometers to meters, you're going to be multiplying whatever value you have by 10 raised to power minus 9. Are you there? So that is why I did that. So let's do that together here. So in this case, delta E now is going to be equal to 6.63 times 10 raised to the power minus 34 times, what's that thing again there? C, 3.0 times 10 raised to the power 8. And I'm dividing this by what? 405. I'm going to multiply this answer here by 10 raised to the power minus 9. Once I multiply by 10 power minus 9, I have already converted the answer to meters. That is why if you should retain the unit, this is joules second. This is joules second, and this is a meter per second. And this is what? Meters. Now you can now see that there will be dimensional accuracy here, because the meters will not cancel the meters, the per second will cancel the second, and your final answer will now be left in joules. Now, how did I get my powers here? All right, so from law of indices, what are the powers here? The powers here are 10 raised to the power minus 34 times 10 raised to the power 8. That's what I have as my numerator. Look at the power, look at it here. 10 power minus 34 multiplied by 10 power what? 8. And I'm dividing this bullshit, sorry, not this bullshit. I'm dividing this thing here now by what? I'm dividing by 10 raised to the power minus 9. Are you guys active? Are you active? Okay, if you're active, respond, I'm active. Let me know you're active because I was answering somebody's question now. All right. Beautiful. All right, so So I'm trying to verify this. So how did we get 10 to the power minus 19? Let's do the math together. Let's do the math together now. Look at my calculator. Let me see. Where is my calculator? You don't lose. Yeah? Okay, I don't see it. Now, look at my calculator here. Now, let's do this together. Now, let's say, you have 10 power minus 34. Now, from law of indices, if you are multiplying, you're adding the index. So I basically have minus 34 plus 8. That's equal to what? Minus 26, right? Now, what I have here is division. Division sign simply means minus. So what I have here is minus 26. So look at what I have, minus 26 minus into minus what? 9. That's what I have here. Because check this out. So this is, I got minus 26 as my numerator, and the division sign here means what? Minus. And I'm trying to collide it with what? Minus 9. What would that give me? That will give me minus 26 plus 9. So minus 26 plus 9 is equal to minus 17. So whatever answer you get from this question on top here, the power is going to be minus 17. And what is that going to be? Let me check. Let's just do it together. So I'm now going to get 10 raised to the power minus 17. So let's work this out. So I'm going to have 6.63 multiplied by 3. So now I'm going to be working on just the numbers, not the index, because I've already taken care of the index. So 6.63 multiplied by 3 is equal to this, divided by, what do I have here? I have 405. So that gives me, look at it here, 0.0491. So I have 0.0491 times what? Times 10 raised to the power minus 17. Now, how do you now take this answer here to standard form? Because you cannot report this answer like this. It does not make any sense. How do you take it to standard form? Now, you're going to go 1 and what? 2. And that will be 4.91. Since you went forward 2 times, you do minus 2. And that will give you times 10 raised to the power minus 19 joules. Final answer. Now, this was the calculation I was doing somehow in the background, which I didn't want you to see because it was not necessary at all. So who has further questions to ask? All right, so this will be the end of our live for today. And we are going to be doing the experiment 9 tomorrow. And I'm going to notify you when that will be on the group chat. So please stay active. I'll be dropping it, I think, in a few minutes time from now. Now, someone is asking questions about the spectrum color. Now, look at the spectrum color here. For the spectrum color, you don't need anything. Now, spectrum is totally empty. We are not going to fill anything here because the instruction did not ask us to fill anything in the spectrum color. So the spectrum color is going to be left blank. Don't fill anything here. So that is all about this. So don't fill anything in the spectrum. Spectrum is empty. Don't fill anything here. All right, so that is all for our live for today. So I'm going to see you tomorrow for more. Have a wonderful night, everybody. Good night. Thank you for sticking around. All right, you guys are highly welcome. Highly welcome.